Hey, welcome to Unit 2, Part 4, the last part for Unit 2. Basically, in this lesson, we are going to talk about the periodic table and the different families of the periodic table. There's quite a bit of information, so let's get to it. First, we need to discuss what are the horizontal rows and the vertical columns called. Periods are the horizontal rows that go left and right. Periods tell us how many energy levels an element has. Sometimes they're called electron shells. So if I look here at this little blank model of the periodic table, if I'm in period 1, there's only one energy level. If I'm in period 2, I'd have two energy levels. If I'm in period 5, I would have 5 energy levels. Let's take an element at random. Let's say I want to look at aluminum, which would be right here, and I'll pull up in a second. We're going to look at a model of aluminum. Now, we saw in the very first part of Unit 2, which is the history of the atomic theory, Tyler DeWitt showed various different models. We use different models to represent atoms based upon basically what we know at the time and how much information we really need. We are going to use Bohr models, which are not the most accurate. However, they do help simplify a basic understanding of an atom. So, aluminum, again, is right here. It's in period 1, 2, 3. Notice it's in the third row. That would be, again, third period. So it should have 3 energy levels. Well, if I look at a Bohr model of that, we'll notice that yes, it does. Here's the nucleus in the center, and around that are these energy levels. And sure enough, aluminum has 1, 2, 3 energy levels. And on each energy level are the electrons. Now again, are electrons truly actually stuck on these little orbits, these energy levels? No. We saw in a previous video that the electrons can be all over. They're kind of like in a zigzag buzzing pattern. They can be anywhere and everywhere. Quantum mechanical theory states that electrons can be here, there, nowhere, and everywhere at the exact same time. It's kind of crazy. But again, period 3 has 3 energy levels. Let's pick a different one. Let's pick carbon. Carbon, which is right here, it's in period 1, 2. Notice the period number right here. It's in period 2. So it should have how many energy levels? Yes, it has 2. 2 energy levels. And if I look at that, 1, 2. Again, we have the nucleus in the center, and we have 1 energy level, 2 energy levels around it. So that's what the periods tell us. Families are the vertical columns. Basically, a family, sometimes they're called groups. Elements that are in the same family behave the same because they have similar chemical characteristics, and there's a reason why. The reason why they behave the same is because they have the same number of valence electrons. Now, why do you think they call them families or groups? Well, they're called families or groups because think of your family. Many people look like their family members. Many people act like their family members. Groups. Think of your group of friends. Usually you hang out with people who act a lot like you. Not always, but sometimes. The elements that are in the same family, the same column, for the most part, look alike and act alike. That's what makes them families or groups. So, again, why? It's the number of valence electrons. Now, how do I find the number of valence electrons? It's really, really easy. Basically, at the top will be numbers, which I'll show you here on this periodic table. For example, this is family 1 or group 1. Sometimes it's 1A, sometimes it's Roman numeral 1A. You'll notice that on this periodic table, it goes 1, 2, then 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Or they use Roman numerals 1A, 2A. These are all down. These are the B's. We'll talk about that later. Then Roman numeral 3A up to 8A. Or they say just 1A through 8A. The most important part is this number in front of the A. If it's 2 digits, like the 13, 14, 15, 16, 17, 18, you do the number in the ones place, which again for 13 would be 3. For 16, it would be the 6. This number tells you how many valence electrons there are. So everything in family 1A has 1 valence electron. every single element in family 3A has 3 valence electrons. And let's look at that. Aluminum is in family 3A. And if I pull up the picture of that again, we can see this. Valence electrons are the outermost electrons. Again, they are the electrons in the outermost energy level. 1, 2, 3. It's in family 3A, therefore there's 3 valence electrons. Carbon was in family 4A. So how many valence electrons would carbon have if it's in family 4A, or 14, or Roman numeral 4A? Good, it should have 4, and let's look at that. Here's the outermost energy level, it's the one farthest away from the nucleus, and sure enough, 1, 2, 3, 4 valence electrons. Okay, so again, periods, left, right rows, families and groups, up, down, columns, vertical. Next, how is the periodic table really arranged? Well, the periodic table is arranged by increasing atomic number. And if we look at the periodic table, you'll notice that this whole number at the top left corner of each one, that's the atomic number, which again tells us the number of protons. If you look, this number always goes up by 1. It always goes up by 1 until you get to down here. Then it does something kind of funky. It warps down. Technically, these two rows right here actually fit in the periodic table right here. The reason why we don't show that, though, is because otherwise the periodic tables would be really long, and they just do this to save, space on paper. But the atomic number always goes up by 1. It never goes down. Also, we have repeating periods. Remember, periods are the rows. Basically, what it's saying is every row repeats a pattern. So an easy way to kind of visualize this is I always try to explain the periodic table as if I was teaching kindergartners. And kindergartners know shapes. So how do I show increasing atomic number? By showing bigger and bigger and bigger and bigger elements. So it goes from a small square to a slightly bigger circle to a slightly bigger triangle, then a slightly bigger square, slightly bigger circle, slightly bigger triangle, so on and so on. The repeating periods. Notice the pattern. Square, circle, triangle. Then I start a new period. Square, circle, triangle. Then I'll start a new period. Square, circle, triangle. And if I was to start another period, you know what the shapes would be and what order they would be in. It's pretty obvious because the periods repeat. And if I look at the periodic table, we'll talk about in a little bit that these are the alkali metals, then the alkaline earth metals. There's nothing here, but if we were to be down in period 4, transitional metals, then it goes these non-metals, blah, 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 halogen, noble gas. So again, a common pattern is alkali, alkaline earth, transition, halogen, noble gas. And it keeps repeating that pattern over and over and over again. So that's kind of how we set up the modern periodic table. Okay, let's talk about where are metals, nonmetals in the semiconductors. So metals, I'll use this periodic table to kind of show this. On many periodic tables, there's a dark kind of printed staircase looking zigzag. So it starts right here. If you follow my mouse cursor, you can see it. This is the boundary between the metals and the nonmetals. All the elements that are in red are metals. So basically, any element to the left of this staircase, with the exception of hydrogen, are metals. And if you notice, that's a majority of the periodic table. A majority of elements are metals. So anything to the left of the staircase, with the exception of hydrogen, are metals. Anything to the right of the staircase is a nonmetal. And then some of the elements that are kind of touching the staircase, they're in between. They're called metalloids. They're kind of like half metal, half nonmetal. Sometimes they're called semiconductors, which I'll use the word here in notes. They're called metalloids, or I call them semiconductors. But what are some characteristics of metals? Well, metals are good conductors of heat and electricity. Most of them are very shiny solids, except for mercury, which is a liquid at room temperature. They can be stretched in shape. Remember, that's malleable. And most of them are found on the left-hand side and the middle of the periodic table. They're all to the left of the staircase. Nonmetals are basically the opposite of a metal. So nonmetals are metals that are bad or poor conductors of heat and electricity. They're insulators. They're dull. They're not shiny, they're dull. Instead of being malleable, they're brittle. And with the exception of hydrogen, they are found on the right side of the periodic table. Semiconductors or metalloids are elements that are in between. Okay, they're intermediate conductors of heat and electricity, meaning they conduct heat and electricity under certain circumstances. And again, they're found on the border, and there's only 6 of them: boron, silicon, germanium, arsenic, antimonium, tellurium. And if I also pull up that one periodic table, which I don't know if it's, oh, I can use this one. So boron, silicon, germanium, arsenic, antimonium, tellurium. I don't like this periodic table as much as the other one. Ah, there we go. It's these yellow elements right here. So again, we have the metals, metalloids, nonmetals. Now, let's talk about individual families on the periodic table. There are basically 5 main families I really want to get into. We're going to start with the alkali metals, which are found on the far, far left of the periodic table. They're in family 1, or 1A. Since they're in family 1A, they all have 1 valence electron, because again, the number next to the letter A tells you how many valence electrons they have. These are actually very soft and shiny metals. They almost cut like clay or Play-Doh. The farther down you get, the softer they get. But they react violently with water. I mean, you put them in water and they just poof. And the farther down you get, the more explosive they get in water. And again, they're also not just in water, they're also just very extremely reactive. They're basically never found by themselves in nature. They react with everything. Sodium, which I have some in my chemical closet, they have to store that in oil, because if it's not in the oil, if it's just in air, it will react with the oxygen in the air. So again, alkali metals are family 1. Right next to them, in family 2, are the alkaline earth metals. And because they're in family 2, they have 2 valence electrons. They are less reactive than the alkali metals, but they're still pretty reactive. Again, this includes magnesium, calcium, which is in your bones, and barium. So I can show that here. So we have beryllium, magnesium, calcium, strontium, barium, radium. So again, family 1, alkali metals. Family 2, alkaline earth metals. This says alkali earth. I say alkaline earth metals. Then we get to the whole middle parts. Sometimes these are called the B elements. These are called the transition metals. These are the metals you probably know very well. They are very unreactive, and they're very good conductors of heat and electricity. Examples of gold, copper, iron, chromium. Let's see if I can find another. Cobalt, titanium. These are the very common silver. These are the common elements that we know of for like jewelry. You would never want to wear an alkali metal for jewelry, because if that touched your skin and their skin was wet, it explode, it would react. You won't want to wear jewelry that blows up. No, that's why we use transition metals, because they're unreactive for the most part. Then we're going to kind of skip these families right here. Families 3A, 4A, 5A, 6A. I mean, they really don't have technical names. I mean, I've seen been called the boron family, the carbon family, the nitrogen family, the oxygen family. But they're not really special like the other families are. So when we get to 7A, these are the halogens. Some people call them halogens. Whatever, to each his or her own. But the halogens are found in family 17, or 7A, which means they have 7 valence electrons. And they are extremely reactive nonmetals. So if you notice, we have the extremely reactive metals. Alkali metals are extremely reactive. And then the halogens are the extremely reactive, well, let me go down here, are the extremely reactive nonmetals. So again, if we notice a period here, this pattern, it goes extremely reactive metal, then it goes not so reactive metal, not reactive metal at all, slightly reactive nonmetal to super reactive nonmetal. Oh, does that mean that noble gases are beyond reactive? No. Actually, no, they're not. The noble gases, which is family 18 or 8A, helium, neon, argon, krypton, they have 8 valence electrons. Now, with the exception of helium, because we'll talk about why later. Because they have 8 valence electrons, they are called inert. Sometimes they're called the inert gases. Inert means they don't react with anything. Now, you can technically get them to react under very certain circumstances, but for the most part, these elements don't mix with anything. They do not react. So again, but why? Because of the 8 valence electrons. Later on, we'll talk about how all atoms want to have 8 valence electrons. 8 electrons in the outermost shell. If they do, they're very, very, very stable. And the noble gases already have 8. So that's why they're so stable. They don't react with anything. What's very also important to know is that any element in family 1A through 8A, these are called the representative elements. So again, I don't know if this periodic table will show it. They don't have the numbers, and I already got rid of the other one, but that's okay. Basically, the elements 1A, 2A, skip over this. The 3A, 4A, 5A, 6A, 7A, 8A, these are the representative elements. The elements in the middle are just the transition metals. So we have representative elements and transition elements. Representative elements, transition elements. And that's it. So that's everything about the periodic table. Kind of a lengthy lesson, but there's a lot to know about the periodic table. Thanks.